everyone, I'm Mariam Mohammed Ilbahar and I'm going to be talking about the restoring force in motion in my physics project. So first I'm going to tell you what is the periodic motion. So basically, periodic motion is the motion that is repeated over a specific amount of time. Periodic motion examples are a rocking chair, a bouncing ball, vibrating tuning fork, a swing in motion, and even the Earth in its orbit around the Sun is considered periodic because it takes a specific time to make a full cycle and then it keeps on repeating for the rest of the life. And a water wave is also considered periodic motion, as if these objects aren't acted upon by any means of friction or air resistance, they would keep moving forever. So that's why it's periodic, because it doesn't stop, it keeps on moving. Okay, there are different types of periodic motion, and the type I'm going to be discussing today is the simple harmonic motion. Basically, in simple harmonic motion, the difference that makes what makes a difference between it and between irregular periodic motion is that it's actually an example of the simple harmonic is an example of the periodic motion. Yet what differentiates between it and between the other examples is that in simple harmonic motion, the force must be acting towards the equilibrium position and must be directly proportional to the displacement and must be to the opposite direction of the displacement. So if the force is in to the same direction of the displacement, therefore it will be periodic yet not simple harmonic. Simple harmonic motion. In mechanics and physics, simple harmonic motion is a special type of periodic motion where the restoring force on the moving object is directly proportional to the object's displacement magnitude and acts toward the object's equilibrium. So if the displacement increased, the restoring force would increase as well. If the displacement decreased, the restoring force would decrease as well. So here are the examples of simple harmonic motion. The first one is the horizontal mass spring system. So as you can see in the first one, it is in the equilibrium position. The second one, it is stretched. And the third one, it is compressed. Well, apparently the distance that by which it is stretched is the same one by which it is compressed, and the restoring force would be the same too when it's at the maximum displacements, okay? But one would be negative and the other would be positive because they're the same displacements, so the restoring force are the same too, yet opposite in directions. So first, at the first one, the equilibrium position, of course, the force is 0, the displacement is 0, and the velocity is 0 too. The second condition, the force would be maximum because it is not stable, so it wants to return it to the equilibrium position, so the force is maximum. Yet the velocity is going to be 0. And once the velocity is 0, the kinetic energy would be 0 too, and the potential energy would be the maximum because potential and kinetic make the mechanical, and the mechanical is stable. So once the kinetic is 0, the potential must be maximum. Okay, so in the second one, in letter B, the velocity is 0, kinetic energy is 0, potential energy is maximum, force is maximum too, and once the force is maximum, the acceleration must be maximum as well, okay? Once it returns to the equilibrium before being compressed, the velocity would be maximum. That's why it will complete moving rather than stop because of the momentum and velocity. So the velocity will keep it moving, and the momentum and the inertia would not be capable of stopping its motion because they're existing. Okay. At this moment, there is no restoring force and no acceleration because it's already at the equilibrium position. So the kinetic energy would be maximum and the potential energy would be 0 because of maximum velocity as well. The third one, when it's compressed, the velocity would be 0 because it will stop at an instant and then return to the right. When the velocity is 0, the restoring force is maximum, acceleration maximum, and the kinetic energy is 0 too, potential energy is maximum. Here is another example, which is the pendulum. Now let's explain more the spring force. The spring force is exerted it's exerted towards the equilibrium position when the spring is stretched or compressed by any force. Okay? An object that compresses or stretches a spring is always acted upon by a force that restores the object to its rest or to the equilibrium position. Hooke's law and the phenomena of simple harmonic motion help us understand the physics associated with elastic objects. Here is Hooke's law experiment. So as you can see, first there is this spring and the unknown mass, and this meter stick is actually like a ruler, and these other things on the left are what actually ensures that this would not move, so the experiment would be perfectly done. So basically, the unknown mass is attached to the spring, that's why it's going to be stretched. So the meter here would prove for me that the amount stretched, the displacement would be the same exact one as the displacement compressed. And it will prove also that the weight of the object that pulls it downwards would be equal to the restoring force, but in opposite directions. Equation of Hooke's law. For most springs, specifically for those that are said to obey Hooke's law, the magnitude of the force is directly proportional to the amount of stretch or compression of the spring, which is the displacement. So as you can see, the force must always be directly proportional to the displacement, and that's why Hooke's law has been derived. The variables of the equation are: F represents the force, K spring constant that measures how stiff and strong the spring is. And the displacement is the distance, the X is the distance traveled, the distance the spring is stretched or compressed away from the equilibrium or rest position. Apparently the spring constant refers to the stiffness of the spring, which means if it is very high, so it's gonna need more force to be stretched and to be compressed. Okay, if it's very low, it will be easily stretched and compressed. The units force is Newton, spring constant, newtons per meter, displacement meters. So here is an example in order to ensure that you understood very well. A load of 45 Newton attached to a spring that is hanging vertically stretch the spring 0.14 meters. What is the spring constant? So as we know, F equals to negative kx. We have the force and we have the meters, the displacement, so we could just divide the force with the displacement, and then we're going to find the spring constant, which is 320 newtons per meter. A vertical mass spring system. In this case, the restoring force would be equal to the weight of the object, and that's something I've said before when I was explaining the mass spring system, that the restoring force would be equal to the weight, but in opposite direction, because it's stretched downwards. The weight, the gravity pulls it downwards, so the weight will be downwards, and the restoring force, of course, will be upwards. So the restoring force is negative, the weight is the restoring force is positive, I'm so sorry, and the weight is negative. Here's an example. The spring, once we put the mass, it's going to be stretched a little bit, and then this would be its equilibrium, the new equilibrium, and then it's going to be stretched and compressed to based on the new equilibrium, not the old one. Okay, so what's gonna basically compress it and or stretch it is the weight. So the weight of the mass would be the force that pulled it downwards, and the restoring force is gonna return it and make the periodic motion. The pendulum's restoring force. A pendulum is the weight suspended from a pivot so that it can swing freely. When a pendulum is displaced sideways from its resting equilibrium position, it is subject to restoring force due to gravity that will accelerate it back to the equilibrium position. The restoring force at this condition is the x component of the gravity, as it's the only force that restores it back to the equilibrium position. The restoring force of the pendulum is here, as you can see. There are no other forces that would return it to the equilibrium position other than the x component of the gravity. That's why this is considered the only restoring force in this situation. Thank you for listening.